In this section, we'll break down embeddings in LLMs in a practical, interview-focused way. We'll start with the core idea of how tokens become vectors through lookup tables, then connect that to how embeddings are trained, used, and deployed in real systems. The goal is to give you both the intuition and the engineering trade-offs you'll need for AI engineering and LLM interview discussions. What interviewers usually want to test here is whether you understand embeddings beyond the buzzword. First, define them clearly. Token IDs are mapped to dense vectors through a learned lookup table. Next, separate static token embeddings from contextual representations, which are hidden states shaped by attention. You should also know how embeddings are initialized, including scaling and weight tying. And finally, connect all of that to real systems, like adding vocabulary and making deployment trade-offs. The embedding layer is basically a lookup table. It takes a discrete token ID and maps it to a learned dense vector. Internally, it stores a matrix with one row per vocabulary item and one column per embedding dimension. When you pass in token indices, it simply retrieves the matching rows rather than computing them from scratch. In PyTorch, this is NN for embedding. You can think of it like a dictionary. Token ID in, vector value out. A common interview confusion is the difference between a token embedding and a hidden state. A token embedding is the token's initial vector, pulled from a lookup table so it starts out static. A hidden state is what that vector becomes after passing through attention and other layers. In other words, embeddings are the starting point, and hidden states are the context-aware representations the model actually uses to make predictions. This slide shows how text moves through a transformer. We begin with token IDs, which are discrete symbols from the tokenizer. Those IDs are converted through an embedding lookup into dense vector representations. Then positional encoding is added, so the model knows the order of the tokens. From there, the embeddings enter the transformer layers, where every later computation builds on this first mapping from tokens into continuous space. One important shape distinction in Albert is between embedding size and hidden size. Albert separates these on purpose. Embeddings are context-independent representations of tokens, while hidden states are context-dependent and evolve through the network. That matters because it shows embeddings are just the model's starting point, not the full model itself. Understanding that difference is a good signal that you grasp how information actually moves through the architecture. Here's the interview trap. Not all LLMs use the same embedding initialization. BERT and GPT-2 though typically use a normal distribution with mean 0 and standard deviation 0.02, controlled by the config. T5 is different, using a much larger standard deviation scaled by an internal factor. And in plain PyTorch, trainable weights are randomly initialized, while the padding index row stays 0 and doesn't get updated. So the strong answer is, initialization is model-specific. Weight tying means the model uses one shared matrix for two roles, turning tokens into embeddings on the way in, and projecting hidden states to next token logits on the way out. In GP2, this is the default. It saves parameters and often keeps, or even improves, language modeling performance. But there is a trade-off. Early in training, output-side gradients can dominate, so that shared matrix is learned more for prediction than for building high-quality input representations. Here's a quick rule of thumb for when to bring up weight tying. It's most useful in architecture knowledge questions and system trade-off discussions, and anytime someone asks about model size versus quality. The classic reference is the Press and Wolf paper, which showed that tying input and output embeddings can improve parameter efficiency in language models, often with little or no loss in performance. Here, we're expanding the model's vocabulary. We start with a pre-trained language model whose original vocabulary stays fixed, then initialize the new tokens, either with random normal values or, preferably, a mean-based approach. After that, we resize the embedding matrix using resize token and claddings to add the extra rows. For causal language models, Mean-based resizing is usually best because it keeps next token probabilities more stable when adding domain terms, tool markers, or multilingual tokens. When adding new tokens, initialization matters more than people think. A simple option is random normal initialization with zero mean and a standard deviation set by the model config, but that can disturb the model's existing token probabilities. A better default, used in Hugging Face, initializes from the mean and covariance of the current embeddings. That reduces distribution shift and usually leads to more stable fine-tuning. Understanding that trade-off is important in applied LLM work. Here's the implementation path in Hugging Face transformers. The model's custom initialization logic lives in init waits. After the model is constructed, post init runs that initialization and also handles wait tying. If we need to change the vocabulary size, resize token embedding safely adds or removes embedding rows, and tie waits explicitly links the input embeddings with the output projection, so those parameters stay shared where the architecture expects it. Here's the side-by-side picture. BERT, GPT-2, and T5 all use normal initialization and all tie weights in some form, and in these standard setups, embedding size matches hidden size. But the key difference is how initialization scale is controlled. BERT and GPT-2 expose an initializer range, while T5 uses an internal factor. That's exactly why broad claims are risky. Details like this really do depend on the architecture. Here are 3 predictable interview questions about embeddings. First, what is an embedding in an LLM? It's a learned dense vector retrieved from the token embedding matrix using a token's ID. Second, how is it initialized? Typically with random values at model construction, using a model-specific scale, like a standard deviation of 0.02 in BERT or GPT-2. Third, is an embedding the same as a hidden state? No. Embeddings are static, while hidden states are contextual. Here are 2 predictable questions. First, why tie the input and output embeddings? It cuts parameters and usually keeps model quality about the same. But in practice, the output side gradients tend to dominate training. Second, what happens when you add tokens? You have to initialize new embedding rows, and for causal language models, mean-based initialization is usually more stable than a random normal. Strong answers go beyond definitions and explain the engineering impact. Here are 3 portfolio projects that really stand out. First, build a mini transformer from scratch and clearly document how you initialize embeddings and how those choices affect behavior. Second, run a token expansion experiment by adding domain-specific tokens to a pre-trained model and comparing random versus mean-based initialization on downstream loss. And third, analyze tied versus untied embeddings by training a small language model, measuring perplexity, and inspecting the resulting embedding geometry. This slide is really about judgment. In the embedding layer, every design decision comes with a trade-off, whether it's speed versus flexibility, memory versus accuracy, or simplicity versus scalability. Interviewers look for candidates who can explain both the benefit and the cost of a choice. That's what signals real practical understanding, not just familiarity with the terminology. The key boundary in an LLM is where visible tokens become vectors at the embedding interface, and everything after that is dense computation. That sounds simple, but it drives real engineering decisions: how embeddings are initialized, how vocabulary changes are handled, and what breaks at deployment when tokenization and model weights don't line up. If you can reason clearly about that boundary, you're thinking like an LLM engineer. What strong candidates do differently is pretty consistent. They trace the actual implementation, and they verify things like initialization in the source code or official docs instead of repeating hearsay. They explain the engineering consequences, connecting choices like weight tying or a knit scale to real behavior. They also avoid overgeneralizing, because a good answer often is, it depends on the architecture. And finally, they show working projects. Reproducible experiments beat memorized answers every time. Here are the key takeaways. First, embeddings are really a lookup table, not a computation step by themselves. The contextual meaning comes later from attention layers. Second, initialization is model-specific, so don't memorize one rule. BERT and GPT-2 use 0.02, while T5 is different for good reasons. And finally, weight tying saves parameters, but it also changes learning dynamics. In practice, real embedding experience comes from building and analyzing systems, not just defining terms.